Now, I'd like to go through the argument in a fairly simple-minded way as to why the Coulomb repulsion becomes ineffective when you put the deuterons into periodic states. Okay, the normal repulsion in the helium atom, where they're in a single, electrons are in a single volume, is that you have a repulsion of E squared over R12, which is the separation. And there's a singularity in the Coulomb repulsion at that point. Now, if the charge, however, is distributed into n-cell unit cells, then the charge in each unit cell is just, instead of E, is E over n cell, and the Coulomb repulsion in one single unit cell is E squared over R12 divided by n cell squared. But electrons, particles that are divided into many unit cells, they're still the same particle. They're still a piece of quantized matter, and the little pieces of the particle in each unit cell act coherently. They're in lockstep. And which means that you have to, if you're going to get the full repulsion on the particle, you have to add up the effects in each of the n-cell unit cells, and that means that you have to multiply this by n cell. And so the contribution to the system potential energy really is decreased by 1 over n cell rather than by 1 over n cell squared. Well, this, in large crystals, this 1 over n cell decreases the potential energy without affecting the kinetic energy. And at very large crystals, basically the effect of the repulsion becomes so small that basically the protons, the deuterons, are uncorrelated. They're almost as if they were neutrons in a band state. There's no repulsion really keeping them apart. And on the other hand, if you go to smaller crystals, then this correlation avoidance becomes deeper and deeper until it goes down to 0. And when that happens, nature no longer accepts that kind of solution. It no longer gives the minimum energy condition. And at that point, nature switches to side-by-side configuration, which is really saying that at that point, you go from a solid-state periodic picture to the chemical picture where the deuterons are localized. And however, in the larger crystals, when nature chooses correlation avoidance, then appropriately paired with appropriately paired nuclei, those with opposed nuclear spins, or ones that form S states basically, the nuclear attraction force is brought into play. And I want to end with just one picture. I want to go back for one stage and look at the helium thing again. I can find it here. Okay. The type of wave function which we're concerned with a two-body wave function, one part giving the position in physical space and the other position in parameter space. That's the same form of wave function that you use for the case of deuterons in block states in a metal. Now, the point is, this theory, that, as we've described, is that both of these wave functions are, both of them are block functions. Now, if you put two uncorrelated electrons in the metal, you have two electrons described by independent block functions. And to our view, when you rearrange this picture or write the mathematics more in terms of what the real situation is in this case, both of these need to be block functions. And this final view graph shows what the general picture of the wave functions are in this case. You can visualize the distribution in physical space is just like the electrons, with each unit cell having an equal amount of charge. And the G of R function that modulates the amplitude of that, if it's a block function, then it also has n cells in separation space, as we call it, and these n cell cusps are the points at which they're n cell such points at which avoidance is created and the wave function amplitude is reduced. So this follows, if you can write the two-body wave function as the product of two block functions, then this theory occurs. And so really the question that cold fusion gives to us, where it tells us, where it impacts physics, is whether this expression that we just had up there is probably described by the product of two block functions. So I view cold fusion as a test of the effect of symmetry on two-particle wave functions. So I think that's all I should go into today.
Dr. Chubb, straighten something out in my mind. This is a beautiful theory. But if I'm correct, the deuterium, the two that come together, have to lose some mass in order to create the energy that goes into the creation of the helium. In other words, the egg has to come before the chicken.
They have to, in the process, they lose mass, right?
Now, I don't quite understand your statement about the helium when the other has to precede it.
Well, if two deuterons come to create a helium and it's created with excess energy, at that time there's no loss in mass. The loss of mass occurs. Now wait a minute. The loss of mass occurs.
Go through that slowly.
Okay.
When two deuteriums come together.
Yeah.
All right.
Suppose there's no electron
In order to
scattering.
give any energy, they have to lose mass.
No.
Because the helium has less mass than the two deuteriums.
That's the final state of helium has less mass.
How louder?
The final state of helium, the ground state of helium, has less mass than the two deuterons. Absolutely.
So it has to happen before
Now,
the creation.
Let me go through that. May I? Okay. Suppose they come together and they don't lose any energy. Then they go right back where they were, right? If they come together and they don't lose, huh?
I don't think that's possible.
Well, that's the way reactions work. If they don't dissipate energy, they'll go right back. Now, if they lose a little bit of energy, they go back. They lose a very small amount of mass, but they can't go quite back. They have to borrow energy to go back. And they can only stay in that second state for the Planck time, delta E over H or whatever it is. They're caught between this thing.
Okay.
And every time they go back, they lose a little bit of mass, which is in the form of energy that's distributed and transferred to the electrons.
You say they're oscillating between?
They go through, that's the way I like to, it's a semi-classical view, but I like to view it as oscillating.
They're oscillating, you see.
Right.
Between creation and decreation, so to speak.
But it's all over in something like 10 to the minus 12 seconds.
Oh, yeah.
So, whether that's, if you add up all the Planck times, they only amount to about 10 to the minus 12 seconds. So, that's maybe an impure way of looking at it, but I think it's a realistic way.